Welcome to Lecture 25A, and entitled Introduction to Applying the Divergence Theorem and Stokes Theorem in 3D in Physical Problems. So we're now basically taking what we've learned and we're going to see how this actually relates to physics, namely the physical world. So this is material that's coming from reading assignment 5, from the introduction to section 2, parts of section 2.1 and section 2.3. The main objectives being for this particular teaching module are determining what are the classes of vector fields that we're going to be solving, getting some sort of intuition as to how to sketch irrotational and source-free vector fields. Then we'll be looking at the divergence theorem for irrotational field problems and ones in which we can basically exploit high degree of symmetry. And then finally we'll look at Stokes theorem for source-free field problems, and again basically exploiting situation under which on the case where we have a high degree of symmetry. So the basic concepts, definitions and visualization skills include how to basically just do a general sketch of the field, because you need that sort of information to start the problem, and also just the various units and definitions that we'll be using before actually moving ahead on working on problems. All right, so as usual, the second slide is just an outline of the lecture to follow. The first item will be just an overview of reading assignment 5 in terms of the details. Of course, the notes have been extracted from reading assignment 5 in many places, but in some cases you may be required to read some of the sections specifically for quiz-related matters or the final exam. And then the other items that you see there basically follow. So we'll be looking at each one of these items in turn. All right, so next thing is to figure out how we're going to solve problems, particularly how to determine the field F. So it's computing the vector field F when the curl of F and the divergence F are knowns or givens. So we start with the Helmholtz equation, which says that you can decompose any field in terms of a irrotational field and a source-free field. So the irrotational field is described in terms of minus the gradient of a scalar potential, and the source-free field is based on the curl of a vector potential. This is another vector field. So this is more or less a starting point. And so if we now take the curl of this expression, followed by the divergence of this expression, we end up with the two following expressions. The curl basically you apply to the right-hand side, but we know from previous work in assignment 4 that the curl of a gradient is 0, and we're just left with the curl of a vector potential. And this basically we're going to call a new vector, J. We take the divergence, then we'd be taking the divergence of a gradient plus the divergence of a curl. But we also know that this is equal to 0, leaving us just with this term. And this also can be written as the Laplacian operating on a scalar potential. And this basically we're going to call rho. So in an electromagnetics problem, this would be a current flux density. In electrostatics problem, this would be a charge density. So in summary, these are the two equations that are typically given. The divergence of the field is a given. The curl of the field is given, right? And so that next question would be, is the uniqueness of the solution for F? Well, it's guaranteed if rho and J decay at a fast enough rate when approaching infinity, which we call the boundary. And this is a situation that will occur in practice. There are more details in the expanded set of notes, but we're not going to deal with it at this point here. Boundaries placed at a finite distance from the source can also be considered, but this is outside the scope of this course. Again, the detailed notes basically talk a little bit about this, but you're not responsible for it. So the problem statement you'll be given will always have this sort of form. You'll be given a rho and you'll give them a J, and you need to compute F. That's more or less what we're going to be doing. All right, so the class of vector fields F that will be solved. So I've just put in bullet form the different things that are of importance. First of all, solving for F is difficult for the most general of cases, but those are not the cases we're going to consider. We're going to look at problems where we know we have a high degree of symmetry and that the field is either circulation-free or source-free. And then F can be computed, basically making use of what we already know, basically applying a divergence theorem or Stokes theorem. The two
independent case that we will consider, assuming similar conditions are imposed on rho or J, are that the divergence is rho and the curl of the field is 0. This is what we call an arotational field. And the other class of problem is where the divergence is 0 and the curl of F is J. And this is a source-free field. The symmetries that we'd be looking at typically come in different forms. So for example, planar symmetry, cylindrical symmetry, circle symmetry, periodic symmetry, toroidal symmetry, to name a few. There are all sorts of symmetries you can consider, but we're going to take the simplest classes. Note at various points in these notes, the same symbols may be used to describe a different physical property. So for example, we use the symbol R to describe the radius and spherical coordinates instead of rho in order to avoid confusion with charge density, which will be designated as rho. Also, J is used to describe a current flux density for the examples that we're going to be looking at, which are primarily of electromagnetics nature, but can also represent a general vector field in other cases. Okay, so next thing is basically to look at the solution approach accounting for a high degree of symmetry. And so these are the conditions you're looking for. In an appropriate coordinate system, F satisfies the following conditions. First of all, the vector F has a magnitude, which is a function of only one variable. And secondly, the vector F has a direction vector aligned with only one of the unit basis vectors. So if we're dealing with cylindrical coordinates, basically we have the radial component, the theta component, and the z component. So the basis vectors would be either r hat, theta hat, or z hat. That would be essentially, we're talking about basis vectors. All right, so we're going to be using the integral formulation to solve this type of problem. So under the conditions stated above, it's possible to apply the divergence theorem or Stokes' theorem to convert the partial differential equations, that is, divergence of field F equals rho and the curl of F equals J, into an integral form and then solve for F. So for an rotational field, this is basically the differential form. And if we use the divergence theorem, then we basically know that if we take a surface integral, closed surface integral of F over the surface, that's equivalent to taking the divergence of the vector field integrated over the volume dV. But the divergence of field is rho, so this would be like integrating the total charge enclosed within the volume, charge density, which is also called the total charge enclosed. So this is a type of expression that we'll be working with. If, on the other hand, we're dealing with a source-free field, the divergence of the field is 0, the curl of the field is J, and now we use Stokes' theorem. So if I were to take a closed contour integral of f dot ds along the contour, then this is equivalent to the curl of f integrate a dot product with the differential surface area, which basically is bounded by this contour on the left. However, from the expression up here, we know that the curl of f is nothing more than J. And so we can substitute that in here. But if you look at this, J dot ds, this is nothing more than integrating the current flux density over an area bounded by the contour, and this we call the total current enclosed. So these are the two expressions that we're going to be working with. And next term in ECE 221S, these are the sorts of calculations you'll be doing. All right, so let's look at some examples illustrating high degree of symmetry, planar symmetry, cylindrical symmetry. This is also cylindrical symmetry. In this case, again, we're only dealing here at the moment with the XY plane. You can see that the field is only pointing along one direction, either the minus x hat direction or the x hat direction. And so here you'll see that f is equal to f is a function of x hat. All right, and so the fact that we've got this in the direction of one unit vector and only a function of one variable basically satisfies the condition of symmetry that we alluded to in a previous slide. In this case, it's just in the form of a circle. We can write this in the following form. But if you'll note, this here basically is nothing more than a vector field, a unit vector in a form of a circle. And this base square root of x squared plus y squared is nothing more than the radius. So this would be in the radial direction. So we can essentially say that the field is in the direction of theta hat, but its magnitude depends on the radius. So again, this satisfies the condition of the symmetry that we basically considered in the previous slide. In this case, the field is in a radial direction, so we could express it in the following form. This is the unit vector, and this is a function of x squared plus y squared square root. Well, this is nothing more than the radius. So again, it's a function of one of the variables in the new coordinate system, and also as a function of the unit vector, the radial unit vector in cylindrical coordinates. So these are symmetry conditions that typically we'd be looking at. All right, we can also have spherical symmetry. Now this is a three-dimensional problem in this case. So in this case, what we would have is a unit vector pointing in a radial direction if we're dealing with symmetry, a spherical symmetry. And this term now represents the radius, basically in a 3D system, if we're dealing with spherical symmetry. So again, because we have that the field's magnitude depends only on one of the vectors, magnitude of the unit, one of the variables for the new coordinate system, and also the direction of the field is in the direction of one of the unit vectors, namely r hat, means that this is a type of problem that we'll be able to solve. All right, so now just a couple of guidelines for sketching vector fields for F. First of all, the rotational field followed by the source-free field. So these are just general points to observe when you're doing sketches. First of all, in the case of your rotational field, the vector field lines diverge from or converge to the source. Outwards if the scalar density rho is positive, and inwards if the scalar density rho is negative. Second, each differential element of the source can be considered as a point source. So if I had, for instance, a distribution of charges, I could essentially say that that distribution consists of an infinite number of point sources, and each one of those point sources basically would produce a field in line with the first bullet item. And then essentially all these different fields can be superimposed to produce the total field. Thirdly, the field pattern for a point source is a series of lines spreading out radially from the source. And fourthly, the total field at a given point, as we just stated, is the superposition of the field lines from all of the differential sources. For a source-free field, the direction of the flux density J at any given point from a geometrical standpoint, in other words, if you look at it from a geometrical standpoint, it's akin to the direction of a localized axis of rotation. Secondly, the direction of the field is determined using the right-hand rule, which means that the thumb points along the axis of rotation, which is the direction J, and the vector field F forms closed contours in the direction in which the fingers of the right-hand point. The third item is that the vector field F forms closed contours since the field is source-free. Why? Because the divergence F equals 0. And fourthly, the divergence of the curl of a vector field is the divergence of J, which is equal to 0. Therefore, the vector field J must also form closed contours. So when you actually sketch the current flux density, it's implied that the field lines form closed loops. Okay, general note. Regions where the vector field lines are straight, parallel to each other, and spaced equidistantly are regions where the field is uniform. Secondly, regions where the density of field lines increases in a particular direction or where the intensity of the field is increasing. So these are just guidelines that help you determine how to go about sketching field lines. So let's look at the irrotational field case. We have two charges, a positive charge and a negative charge. These are like basically, could try just points. So this is positive, so the field lines basically point outwards. Now this is negative, so the field lines point inwards. And so these field lines basically pointing outwards will eventually point inwards and attach to the minus. So one of these field lines that emanates from the positive charge basically terminates at the minus charge. So this is essentially a very rough sketch of what the field lines ought to look like of this nature. Notice here the line that's halfway between these two charges. This line basically is perpendicular at this point. So this is very generally what you can use to sort of help you understand what the field lines would look. Again, displacement field lines bunching implies a strengthening field. So here they're bunching, so the field gets stronger as you get closer to the positive or closer to the minus. And again, field lines point outwards from a positive source, which is what you see here, and point inwards to a negative source, which is what you see here. All right, what about a source-free field? So this is an example, for instance, the Earth's magnetic field. It appears as if there's a current flowing around in a circle like this. Of course, this is just showing one loop here, but this would be a distribution. So it would be a current flux density distributed all over this volume that you're seeing here. But this is the general direction that we would assume. So first thing to assume here is that the magnetic field lines bunching means a strengthening field. So you'll notice the red lines are the field lines, so they're getting stronger as you get closer to the globe. Secondly, the field lines which are shaded red and the current density J labeled as I, which is this one here, form closed loops. So see this current, this forms a closed loop, and the field lines, these of course will go into the system and come out the other side as well. So the conditions that we spoke about in previous slides, this diagram basically satisfies both conditions, that the divergence of J is equal to 0 and the divergence of the field is also equal to 0. And thirdly, the right-hand thumb points in the direction of I, the current flux through a filament, and the field lines, if this is taken as a current filament, and the field lines shaded in red point in the direction of the right-hand fingers. So if you were to take your thumb and point it in this direction, then basically your fingers would be basically pointing downwards through here. So that means the field lines come through the center, out the other side, and eventually come back, forming a closed loop. So that's a very quick way of assessing the relationship between the direction of the current flux density and the direction of the field lines. All right, some units and definitions just to review. Again, contour integration, its differential arc length is typically given this notation, ds with an arrow over top. Surface area integration, the differential surface area vector at a given point on an arbitrarily shaped surface is just ds with an arrow over top. In terms of terminology, sometimes use dA with an arrow instead of ds or wherever if the differential surface area in 3D is planar. And in terms of vector notation, vectors are sometimes written bold rather than with an arrow over top. So ds with an arrow is equivalent to ds bold, dA with an arrow over top is equal to dA bold, and ds with an arrow over top is equivalent to ds bold. Alternatively, ds bold is equal to the unit tangent vector in bold, ds, dA in bold would be equivalent to the unit vector n in bold, dA, and ds bold, which equals the unit vector n subscript f's ds. So this would be a differential surface area vector for a curved surface, for a planar surface, and this is basically for contour. As far as densities, there are two types of densities to consider. We'll differentiate between the terms scalar density rho and flux density J. The scalar density rho is a scalar valued function, whereas flux density J is a vector valued function. Second, the scalar value function rho and the vector valued function J can either be differentiable, not differentiable, or incorporate Dirac delta distributions, which we'll be discussing shortly. So what are Dirac delta distributions used for? They are used to represent point, line, or filament, planar, sheet, or curved sheet sources for the charge density. Or they represent line, filament, planar sheet, or curved sheet sources for current flux densities. So this would be for the case of applying the divergence theorem. This is the case for applying Stokes' theorem. The closed surface integral over a closed surface S, f dot ds, S is often referred to as a Gaussian surface. So whenever you see something like this, in terms of when we do some applications, and we talk about a Gaussian surface, we're referring to this surface here. All right, so that concludes Lecture 25A. Thank you for listening.